All right, so let's take a look at how the electric field is related to the potential. Um, because work is related to force, so we can actually relate the electric field to the electric potential. So remember, if we look back at our work in energy, remember we would say like, and if we think about a system, the internal energy, we kind of say like the force is the negative change in potential energy, like that, right? Like kind of this derivative. Now, the potential energy, right? The potential energy being Q times the potential there, right? And then the electric force being Q times the electric field. So Q times the electric field, because the electric force is Q times the electric field, is negative the derivative of Q times V. If you treat the charge as a constant, negative Q dV dx, right? You can bring that charge out. And then notice that the Q is going to cancel there. So the electric field is equal to the negative derivative of the electric potential. And it just comes back into unit 3 when we did general forms of work and energy, right? Like that's kind of where that comes from. And then the integral form of that, so if I have that, I can move the dx up, right? Like separation of variables is equal to negative dv. And we can bring the negative sign over here if we want, right? Multiply through by negative sign, and then just integrate both sides. So negative integral of e dx is going to be the integral of dv, which is going to be the change in potential there. So this is the integral form. This is the differential form of the exact same relationship there. Okay. Now, in terms of directions, because this is a vector, I just remember as a rule, electric field points from higher potential to lower potential. So as it relates, if you're given a potential, how do we relate the direction of the electric field? We go from higher potential to lower potential in there, right? Okay, so let's take a look at a few problems here just using some of those principles. Suppose the electric potential is given by that. What is the expression for the electric field in the horizontal direction? Well, that would be the electric field is negative dV dx, which is going to be negative, derivative of that is just 6x there, right? Just like that. Okay, what if it was a vector, right? So the electric field has an x and a y component, is only a function of the x location here. What is the potential difference between here and here? So how would we do that? Again, the way you want to think about it when we're integrating this is just like we did work. Because this is where I really want you to connect this idea, is that this integral here, this is a dot product, is just like we do it with work. That means we care about the components in the x and the y direction, right? So if we think about it on a picture here, we're going from the point 3,3 to the point 6,3. So this is 6,3 over here. This is 3,3. We're integrating. We're taking a path from there to there, just like we would do like a work calculation, right? Now the electric field has components. During this whole time, the electric field is pointing. It has a component in the x and a component in the y direction. So the electric field points like this. And it's given by this vector, right? 2x in the x direction and negative 3x squared in the y direction, right? This is the component, right, notation translation there. So when we're doing this integral, this change in potential, we only care about the component that's parallel to the displacement that we're going through. So we're integrating from here to here. We're going from there to there. We only care about the x component because we're integrating in a path that is in the x direction, right? And so that's going to be the integral of 2x, right, dx. And we're going to integrate over the x coordinate from 3 to 6 there, right? That's what I have to think about that. So that's going to be negative x squared from 3 to 6, right? And so it's going to be negative 6 squared minus negative 3 squared. And so that's going to give you, what, negative 36 plus 9, negative 27, I guess. Negative 27 volts, I guess. I didn't give you a unit in this one, so something like that. Okay, what's the potential difference between going from here to here? If we're going from 3,3 to, say, 3,6, then we're taking a path this way, right? And so if we're going to do the exact same integral, the dx doesn't indicate like, oh, just x direction. It's just the path. X is just indicating the direction you're taking the path. Now we only care about the component of the e in the y direction, right? So we're going to integrate from 3 to 6. We're integrating over the y coordinates. Okay. Now in this case, keep in mind this x is based on the x location. the electric field in the y direction, it is like this negative 3x squared, if you will, but we're integrating over the y direction, right? We're going from 3 to 6 in the y direction. So the electric field's actually constant this whole time. Because, you see, in this problem, the x was varying. So we're integrating over the x because the x varied from 3 to 6. Here, the x is constant. So here, x is constant. X is definitely equal to 3 because during this entire path, right, it's 3 the whole time. So that's going to be negative integral from 3 to 6, and just plug in 3 here. That's going to be negative 27 dy. That negative will cancel with that, and so this is going to be 27 times 3. Or you can do times 6 and then times 3 and then subtract them, which is going to be 54 volts, like that. So that's kind of how you use that integral, right? When you're going from that path to that other path there, like that. Like you're going to be thinking about it. You got to be very careful what the x's and the y's represent when you're doing something like that, okay?